Welcome to Chapter 19 on reinforcement learning and Q learning. Here we shift from systems that simply predict to agents that learn to make good decisions over time. Almost everything we have built so far in this book predicts. Now the setting becomes a loop rather than a one-shot prediction, and we will keep the mathematics light and learn by doing. By the end of this chapter, you should be able to explain the basic idea of reinforcement learning and how it differs from supervised learning, describe the multi-arm bandit and the exploration versus exploitation trade-off, and use the epsilon greedy rule with an incremental average update. You should also be able to explain what a policy is, describe long-term reward, the return, and the discount factor, sketch the Markov decision process framework, and read value functions, Q values, and a state action Q table. This figure shows the reinforcement learning loop. At each step, the agent observes a state, takes an action, and receives a reward, and the next state from the environment, and its goal is to learn a policy that maximizes reward over time. So, what is reinforcement learning? It is a type of machine learning in which an agent learns to make sequential decisions by interacting with an environment, receiving rewards or penalties, and adjusting its behavior to maximize total reward over time. What sets these problems apart from the rest of the book is that decisions are linked across time, so a choice now shapes the situations we will face later. A one-armed bandit is an old nickname for a slot machine, the lever on its side being the arm. This little puzzle is the simplest interesting problem in reinforcement learning, and it isolates the tension between using what you know and finding out more. The sensible thing is to keep a running average of the payoff each lever has given you. To exploit is to pull the lever with the best average so far, the greedy choice. To explore is to try a different lever in case it is secretly better. The standard recipe is the epsilon greedy rule. Otherwise, we pull the lever with the best average so far, which is exploiting. So with probability, epsilon the agent explores, and with probability 1 minus epsilon, it exploits. We do not have to store every payoff to keep each lever's average current. The update nudges the old estimate toward the latest payoff by a step of size 1 over n, where n is the number of pulls. Suppose the four levers have true mean payoffs of 1, 1.5, 0.7, and 1.2. If we knew these values, we would pull lever 2 every time and average 1.5 per pull. Here is one simulation of the four-lever bandit using a decaying exploration rate. Epsilon starts at 1 and is multiplied by 0.99 each trial. For each lever, we track the running average payoff and the number of pulls at selected trials. Watch the updates in action. A first payoff sets a lever's estimate directly, and a later one nudges another lever's average part way toward the new reward. Each step just moves the running average toward the latest payoff by the shrinking amount 1 over n. We used a decaying epsilon in that run because, averaged across many runs, it earns the most reward. So, how much should the agent explore? The answer depends on the value of epsilon, and the next slides compare a few choices. With epsilon set to 0.01, the agent explores so rarely that it learns slowly and often never discovers lever 2 at all, the genuinely best option. Reassuringly, the whole bandit algorithm fits in a short loop. This code runs the bandit for 2,000 trials. Each trial, it either picks a random lever to explore or the best average lever to exploit, draws a noisy reward, updates that lever's running average, and shrinks epsilon a little. Then it reports the estimated means and the average gain. The key point: the bandit strips reinforcement learning down to a single, repeated decision. Exploit the best option so far or explore for a better one. Always exploiting can trap you on a lucky-looking dud, while a little exploration, spent early and then tapered off, finds the best option in the long run. Two parts make up every reinforcement learning problem, and getting them straight makes everything else easier. The agent is the decision maker, the learner, and a robot navigating a room makes the roles concrete. In that picture, the robot is the agent and the room is the environment. Its location is the state. Moving up, down, left, or right are the actions. Reaching the goal gives a positive reward, and bumping an obstacle gives a negative one. Crucially, the agent learns almost nothing from a single step. Understanding comes only from many interactions over time. Three quantities flow around the loop, so it is worth pinning each down. A state describes the current situation, an action is a choice available to the agent, and a reward is the environment's feedback saying how good or bad that action was. The bandit, notice, had no state at all. The loop runs in a clear sequence. The agent observes the current state, chooses an action, the environment returns a reward, the environment transitions to a new state, and then the whole thing repeats. This figure shows reinforcement learning in a changing environment. The agent takes an action in the starting state, producing a reward, and a new state, then acts again, and so on. Because the state changes, each decision reshapes what comes next. It helps to contrast reinforcement learning with the supervised learning that fills most of this book. Here, there is no labeled correct answer. Feedback comes as rewards, actions change future states, so decisions are coupled across time, and rewards may arrive long after the action that earned them. On top of that, the agent must balance exploration against exploitation, and it learns through interaction rather than from a fixed data set. These differences make reinforcement learning more powerful for sequential decisions, but also harder to train and trickier to get right. A subtle and important point: the best action is often not the one with the largest immediate reward. Chess shows this vividly, where a player may sacrifice a piece, accepting an immediate loss, to win the game several moves later. A policy is the agent's strategy, its rule for choosing an action in each state. A simple, deterministic policy just maps each state to a fixed move. In state A, move right; in state B, move up; and in state C, move left. A stochastic policy, instead, picks actions according to probabilities, which can be useful for exploration and for environments where a bit of randomness helps. To talk about long-term reward precisely, we need the return, the total reward collected from now until the end. In the discounted version, we weight each future reward by gamma raised to a growing power, and that discount factor sets the agent's horizon. The formal framework behind all of this is the Markov decision process, or MDP. An MDP has 5 ingredients: a set of states, a set of actions, transition probabilities, saying how likely each next state is, a reward function, and a discount factor. The crucial assumption is the Markov property. The future depends only on the current state and action, not on the entire history of how the agent got there. This figure shows a small Markov decision process. In each state, the agent picks an action that moves it to a new state and pays a reward. Reaching the goal pays +1, falling into the trap costs 1, and the agent's job is to find the path that scores best. How does an agent judge whether a situation is promising before reaching the goal? The value of a state answers how good is it to be here. In a grid world, cells near the goal have high value because reward is close, while cells near a trap have low value. The value function rates states, but to act, the agent needs to compare actions. A Q value answers a sharper question. If I am in this state and take this particular action, how much total reward should I expect? With that, the agent can simply pick the action with the highest Q value. We met this dilemma with the bandit, and it returns in every reinforcement learning problem. The standard compromise is again epsilon greedy selection. Explore a random action with probability epsilon, otherwise take the highest Q action, and shrink epsilon as the Q values become trustworthy. For a second example, let an agent discover the game of NIM on its own. The state is the number of matches left. The action is how many it takes, 1, 2, or 3, and the reward is +1 for winning and -1 for losing. The opponent plays at random while the agent uses epsilon greedy choices. Because the reward arrives only at the very end. After each game, we take the final outcome, +1 or -1, and nudge every state action pair the agent actually played toward it. This is the same shape as the Bandit update, with a fixed step size alpha so that recent games count for more. Here is the NIM-Q table at the very start. Every value is 0 because the agent has played no games. Rows are the action, the matches taken, columns the state, the matches left, and blank cells are simply impossible moves. This is the same table after one winning game. Only the 3 moves the agent actually played are nudged toward the +1 reward, shown in bold, while every other cell is left untouched. Now the table after a second game, this one a loss. The 3 moves played are nudged toward -1, and the opening move, having now both won and lost, sits just below 0, while the earlier winning moves remain positive. After 60,000 self-play games, these Q values have settled. Each column is a state, the matches left, each row an action, and the largest value in a column tells the agent the best move from that position. Reading the learned table gives clean play. From 10 matches, take 1. From 8, take 3. From 7, take 2. From 6, take 1, each leaving 5. 9 and 5 are losing positions where no move is safe against a careful opponent. The pattern continues near the end. From 4 matches, take 3, leaving 1 so the opponent must take it and loses. And from 3 matches, take 2, again leaving that single losing match. We now have every ingredient for Q-learning, one of the foundational reinforcement learning algorithms. The mechanism is a running update that moves the current Q value toward the reward plus the discounted value of the best next action, and the bracketed part is the temporal difference error. This figure shows the Q-learning training loop. Acting under an epsilon greedy policy, the agent nudges the relevant Q value toward the temporal difference target after every step, and across many episodes, the Q table converges to the right values. The update rule is easiest to believe once you have run it by hand, so let us trace it through a tiny 4-cell corridor. This figure shows that 4-cell corridor. The agent moves right from the start, cell 0, toward the goal, cell 3, which pays +1, and we will use it to trace the Q-learning update step by step. In the first episode, in cell 0, the reward is 0, and the next cell has no value yet, so its Q value stays 0, and cell 1 is the same. Only in cell 2, where the move reaches the goal, does the value rise to 0.5. So after one episode only, the cell next to the goal has learned anything at all. In the second episode, the signal spreads. Cell 0 is still 0, but cell 1 now sees that cell 2 is worth 0.5 and rises to about 0.225, while cell 2 climbs further to 0.75. So the reward has now reached cell 1, and cell 2's estimate has climbed closer to its true value. In the third episode, the wave continues. Cell 0 finally becomes positive at about 0.1. Cell 1 rises to 0.45, and cell 2 reaches about 0.875. A table collects these values episode by episode so we can watch the progress. This table shows the rightward Q values after each episode. The reward propagates back 1 cell per episode, and the values converge to gamma raised to the distance from the goal. There are 2 natural moments at which to learn, and it is worth seeing the difference clearly. One waits for a full episode, while Q learning takes the other route, updating after every step, which is called temporal difference learning. The learning rate alpha controls how much each new experience changes the current Q value, and it lies between 0 and 1. A large alpha makes the agent update aggressively, learning fast but reacting jumpily to noisy, atypical experiences. We met gamma earlier as the knob on the return. and it plays the same role inside the Q learning update, deciding how much future rewards count compared with immediate ones. In its simplest form, Q-learning stores its values in a Q table, a grid with one row per state and one column per action. Q tables are perfect for small, discrete problems and make the algorithm wonderfully transparent, since you can print the table and watch the agent's knowledge take shape. Deep reinforcement learning marries reinforcement learning with the deep neural networks of chapters 14 and 15, replacing the table with a network when the states are too many to list. The key point: Q-learning's whole engine is one update. Move each Q value a little toward the reward received, plus the discounted value of the best next action. Master that single line, and you understand the core of value-based reinforcement learning, from a tiny grid world up to deep Q networks. Reinforcement learning fits problems where actions shape future outcomes and where the system can learn through interaction or simulation. The applications are wide-ranging: game playing and robot navigation, autonomous driving and continuous control, dynamic pricing and online advertising, inventory control and resource allocation, trade execution and portfolio management, and energy management, traffic light control, and scheduling. The common thread is sequential decision-making under uncertainty, the exact shape of problem that prediction-focused methods cannot address on their own. Reinforcement learning is powerful, but far from a turnkey solution, so it is worth being honest about the obstacles. It can require enormous numbers of interactions, exploration may be costly or dangerous in the real world, and rewards may be delayed or sparse, making the signal hard to learn from. There is more. Designing a good reward function is surprisingly difficult, training can be unstable and sensitive to settings, and real deployment often needs strong safety controls. The exploration problem, in particular, deserves emphasis. For hands-on practice, our environment is Frozen Lake, a classic grid world where the agent must cross a frozen lake to reach a goal without falling through a hole. This code sets up Q-learning on Frozen Lake with Gymnasium. It makes a deterministic lake, builds a Q table sized by the states and actions, fixes hyperparameters like the learning rate, discount, and a decaying epsilon, and then loops over episodes choosing actions epsilon greedily. What is striking is that every concept from the chapter appears here in just a few lines. Training fills the Q table. Now let us read the policy out of it and check that it actually works. This code turns the learned Q table into a readable policy. For each cell, it picks the best action and prints an arrow grid. Then it runs 1,000 greedy test episodes, always taking the highest Q action, and reports the success rate. The grid of arrows shows the action the agent learned for each cell, and on the deterministic lake, the greedy policy should reach the goal essentially every time. The epsilon schedule shapes how the agent learns, so it is well worth experimenting with. This code trains the agent several times with different fixed exploration rates. It runs the same Q-learning loop for epsilon values of 0, 0.1, and 0.5, then prints the best Q value at the start state for each, so we can see how exploration changes what gets learned. With epsilon set to 0, the agent never explores, so if its early greedy choices miss the goal, it may never discover a path at all, leaving its Q values stuck near 0. Consider a case study in inventory reordering. A retailer must decide, day after day, how much stock to reorder. Order too much and storage costs pile up while cash sits frozen. Order too little and shelves go empty and sales are lost. The company wants a policy that makes this call automatically and well. This is a textbook sequential decision problem, which is exactly why reinforcement learning suits it so well. We can map it straight onto our framework. The state is current inventory, recent demand, the season, and pending orders. The action is how much to order today. The reward is profit minus holding costs minus stockout penalties. And the policy is a rule from each state to an order quantity. An agent trained with Q learning, or a deep variant for the larger, partly continuous state space, can learn to anticipate demand spikes and order ahead. The decisive design choice is where the agent learns, since experimenting on real shelves is risky. The next code applies the tabular Q learning of this chapter to cart poll, showing how a discretized Q table can learn a balancing policy even in an environment with continuous observations. This code sets up that cart poll agent. It chops each of the 4 continuous observations into 10 bins so the state becomes discrete, builds a Q table over those bins and the actions, fixes the usual hyperparameters, and loops over episodes, discretizing each observation as it goes. Printing the mean reward every 1,000 episodes makes the learning curve visible. The agent starts with short, chaotic episodes and progressively learns to balance the poll for longer and longer runs. This chapter moved from prediction to decision making. Along the way, we assembled the vocabulary, agent and environment, states, actions and rewards, and the loop that connects them. And finally, we were honest about the limits. For further reading, Sutton and Bartow is the standard textbook on reinforcement learning, covering MDPs, value functions, Q learning, and policy gradients in depth, while Watkins and Diane proved the convergence of Q learning, giving the algorithm its theoretical foundation. There is more to explore. The work introducing deep Q networks showed that combining Q learning with convolutional networks enables superhuman play from raw pixels. Hull offers an accessible business introduction, and the gymnasium documentation and applied PyTorch tutorials round out the practical side. That brings us to the end of chapter 19, where we learned how agents use reinforcement learning and Q learning to make good decisions over time.